The other problem, which I also saw, which we will be talking in great detail in the upcoming lectures. But since you guys have already done a basic course on communication systems, is what we call a diode detector, or since you guys have seen a circuit like that, I'm going to analyze this. So let's say we have a diode and a capacitor like this. If I apply sinusoid as an input to this circuit, let the sinusoid go from V peak to minus V peak. If it oscillates between V peak and minus V peak, what do you think will be the output of this circuit? Assume the diode is ideal, meaning it has zero cut-in voltage. To turn on the diode, you just need a positive voltage across it. It will turn on. If the voltage is even slightly negative, it will cut off. Keep that in mind. So what happens here? Assume the source resistance of your input is zero. Okay, it's just an ideal voltage source, sinusoidal source. So when you're applying a sinusoid, initially assume that the capacitor voltage is zero. As this node voltage increases slightly greater than zero, the diode will turn on. Once the diode turns on, these two nodes are short. Vi and V0 are short. So your V0 will follow Vi. I'm showing V0 on green. It will follow Vi as it is, exactly as it is. Now, when Vi reaches Vp, V0 will also reach Vp at this point. Right? It's a capacitor. It can hold charge. So you have charged this capacitor to Vp volts at this point. Now, suddenly after this point, your input goes to Vp minus, it goes slightly lower than Vp. The instant your input goes slightly lower than Vp, the diode is cut off. Once your diode cuts off, your output voltage has no path to either discharge or charge. So it will stay constant. It will always stay constant at Vp volts. Your input will keep oscillating. Your input will keep oscillating between a positive and negative values. But if you see, right, your input never exceeds. Vi is always less than or equal to V0. Your input never exceeds the output voltage. And therefore, your diode will always be cut off and the capacitor will always store a voltage of V peak. So this circuit is a peak detector. It helps in detecting the peak voltage of a signal. Okay? Or you can also see it as a AC to DC converter, right? Your sinusoidal output is changing as a sinusoid. It's oscillating between positive and negative values. But the voltage across the capacitor is constant, DC. So if I ask you, what is the average charge in the capacitor? What is the average current flowing through the capacitor in the steady state? What will that be? What will be your average current flowing through the capacitor in the steady state? If I ask you that question, what's your answer? Its voltage is fixed, which means charge is fixed. Average current usually means what? Rate of change of charge. Charge is not changing. So what should be your average current? Zero. Is that fine? So your average current is zero. So is this clear, guys? I just quickly proceeded. Is this fine? Your diode is short circuited, and is the explanation fine? You guys have some doubt? You can ask me. Yeah. Yeah. Monarch, is that okay? Or am I? Why is it becoming a constant? See, at this instant, if you look at this, when the see you is this okay? When Vi is equal to V0 until this point, right? When initially output was at 0 volts, input was also at 0. Now input slightly increases. As your input increases, diode is short circuit. So input and output are equal. Now at the peak voltage, your capacitor is charged to V peak volts. It is charged now. It is fully charged to V peak volts. See, one thing you have to keep in mind, current can flow only in one direction in a diode. Ideal diode, current cannot flow in the opposite direction. For this capacitor to discharge, current has to flow in the opposite direction, which is not possible, right? So therefore, this this capacitor cannot discharge. There is no path for it to discharge. For the capacitor to discharge, the only path available here is through the diode, and that it has to flow through in the reverse direction of the diode. Okay, that's it. So because of that, current, your diode immediately, when your input voltage goes slightly less than V peak, your diode will be cut off. Okay, your capacitor voltage is higher because current now has to flow from this side for it to discharge, and that's not possible. So it will be cut off. So it will stay there. So this circuit is called as peak detector. Okay, your voltage is peak is detected using this circuit. It's also used as AC to DC conversion. So you guys should understand that even though this looks like a very simple circuit, right? A modified version of this is used in RF energy harvesting. So sometimes you have these uh, chips with very low power consumption. Okay, you can't afford to put batteries on those chips. Your chips can be so small that you may want to wear them on your body, on let's say on a human body or a sensor somewhere in a remote place. So you can't put a battery on them. If you can't put a battery on them, then see, for circuits to work on any chip, you need power. Where does that power come from? It has to come from some source, right? Some form of energy, the power has to come from. So in these chips, there's extremely low power chips, which can be put on a human body, or where they don't have access to charging, where you don't even have, the chips are so small that you can't house a battery on top of them. If you can't do that, then you have what you call as RF energy harvesting. You rely on the fact that because all your cell phone towers, your wireless devices, they constantly keep radiating, right? They're radiating constantly. So because of that, there is so much of RF power available in the free space, in air generally. So if you put this device, RF power, you can treat it as some kind of a sinusoid. You guys can imagine it like some form of you know uh, amplitude modulated signals. Amplitude modulated signals are like sinusoid. They're a very high frequency carrier. Amplitude is changed very slowly. So for all practical purposes, you can treat them like some carrier signals. From those carrier signals, I will use this is a very simple form of a circuit, some circuit like this, to extract a DC signal. Once I have this DC signal, I will use this DC signal to power my chips, okay, to power my amplifiers and whatever small operations I want to perform. I will use my circuits to power that using this. So that's why it's a very interesting idea. Idea is very simple, but it's useful to know. Even very recent circuits use this same idea. So it's an AC to DC conversion. You can look at it that way, or it's actually a peak detector circuit. It detects the peak value. So now capacitor stores BP volts. Keep in mind, a capacitor is like a battery. Okay, a capacitor is like a battery, so it can store charge. The only problem is capacitors, batteries ideal. For an ideal battery, I can treat it like a capacitor of infinite capacitance. Meaning it can store, it has infinite charge in its store. So even if you connect a resistor, it will be able to supply infinite current, meaning it will be able to supply infinite charge and still not lose any charge. So that's the ideal definition of a voltage source. No, you can picturize it as a capacitor with infinite capacitance. Okay, which means it has boundless charge. If you store some finite volt, 1 volt across this, then the charge stored is infinity. It has unlimited amount of charge. So whenever you are connecting any circuit, your circuit will draw some power. Let's say your CMOS inverter is drawing some power for it to run. Every cycle it will charge its local nodes, right? Half CV square power or CV square power. It'll absorb, and all that power will keep coming from this capacitor, the ideal capacitor. So I'm just giving, and this is a hypothetical understanding of a voltage source. So we'll come back to this circuit now. So you're convinced now that the capacitor voltage will remain constant, and it's called peak detector. And don't think that it's a very old circuit. It is still used in many, many applications. Slightly more complicated versions of this. But the heart of it, the idea is very simple. So as I said, this is used for peak detection and also for AC to DC conversion. So if you see your adapters, your laptop chargers, your motherboards. So when we used to have this blocks called, we used to assemble desktop computers. So they'll have a SMPS called switch to mode power supply block, and they will all contain some form of AC to DC conversions. You have a 50 hertz sinusoidal signal here, which is what comes from, and 60 hertz, I think in US it's 60 hertz. From that, you will extract a DC signal, and this DC signal will now then power all your microprocessors and other LEDs and everything in your on your motherboard. Okay, so in practice, what happens is that you can model your circuits as a resistive load. Resistive load means it's drawing some power as a resistive load. It is also this circuits like this are often used even in what you call as diode receivers as envelope detectors in amplitude modulation circuits. Your first generation, if you see the first generation, in fact, if I have to say that the field of circuit design began with building radio circuits. So in early 1900s, Marconi, the first inventor, he built this receivers for radios using a very simple diode detector circuit. It's essentially this, a diode and a capacitor and a resistor. So now if the moment I put a capacitor, resistor, what do you think will happen? You'll have a sinusoidal signal. Your output will charge till V peak. After that, your input is going to fall down, and your capacitor voltage will stay at V peak, ideally, if there was no resistor. Now, because there is a resistor, what will happen? Your diode is cut off. At this point, when your input signal goes lower, your diode is cut off. Okay, so one of you are asking me a question. When I use the word peak detector, okay, am I finding the time at which the peak is achieved? No, here at peak means it's peak voltage detector. So it's called peak detector, but it's actually a peak. The meaning is that it's measuring the peak voltage of the signal. That's it. It has nothing to do with the time of arrival. No. Yeah. So it's just a nomenclature. Peak detector. You see, time of arrival is that makes no sense, right? It's an analog circuit. So I just need a DC voltage to operate. So I just need to extract the DC out. So I don't really care as long as the waveform can be shifted a little bit. But as long as I get that VP volt stored across the capacitor, that's enough for me. I have stored its peak. Okay, so it's called peak detector. Probably the terminology may be confusing, but remember this terminology was introduced in 1900s, early 1900s, when digital didn't even exist. So yeah. Okay. Is that fine? I mean, your question is that it's a nomenclature. Right? It's a problem of nomenclature. You're asking what time. It has nothing to do with time. It's just that the capacitor stores. It's a peak measuring circuit. You can also use the word peak measuring circuit for it. Yeah. Okay. Or an AC to DC converter. So now in this cycle, when your input voltage decreases, you are left with a case like this. You have a capacitor and a resistor. Diode is open circuit. Now you are left with a capacitor and a resistor. What will happen is that the resistor will now slowly start discharging the capacitor. Now we will make an assumption that this RC time constant, let's assume this RC time constant is much smaller than the signal's time period. Okay, which means the discharge is very fast. See, whenever RC time constant is very small, it means the discharging is very fast. If the discharging is very fast, it means that the moment your diode is turned off, your resistor will quickly discharge this VP volts, and then your diode will start turning on because your voltage across the capacitor has decreased. So what will happen? It will trace the input signal as it is. If your RC time constant is much smaller than the time period of the signal, T, your capacitor voltage will more or less track the input waveform itself because the resistor is constantly discharging the cap. Okay. Oh, I'm sorry. Is this circuit right? Will it trace all the while, or what will happen here? Will it trace even in the negative half cycles? No, right? It will only trace the positive half cycles. Yeah. So you will get a half wave rectifier. You put a capacitor and resistor. So let's say you have a circuit like this, a diode and a resistor. This is a half wave rectifier, right? Only during the positive half cycles, it's like time constant is 0 here. C is 0. So time constant is 0, which means instantaneously the output will just track the input. So you will get half wave rectified output. Okay, this is also an AC to DC converter. So this guy will have a finite average value. Okay, so that's it. So if your time constant is much smaller, then the input tracks as it is. So I don't get this peak detection property. So I don't want that. Instead, I'll ensure that the time constant is actually I'll choose my capacitor in such a way such that the time constant RC is much greater than the time period of your signal. Okay, your time period T of the signal is much smaller compared to the RC. Okay, I'll just finish this problem, guys, and then we'll leave for the day. So in that case, what would happen is that your capacitor will be slowly discharged like this. It will be slowly discharged. And when your input signal reaches a level where it's greater than the cap, then your cap voltage will start tracing your input signal. Then once it reaches its peak, then it will discharge. So the voltage will look something like this. It will reach a peak, discharge slowly, reach a peak, discharge slowly, and so on. Right? So the waveform will look something like this. So this is 0 volts. I'm just showing on a different color. So if you see, right, there is a finite average value for this waveform. So when you actually convert AC to DC, your DC signal will not be a perfect pure straight line. That will never happen. Your DC signal will have what we call as ripple. It will have this small undulations on top of it. It will be a DC and some small variations like this. And the rate of this variation will be equal to the input frequency. So normally, if you're deriving your DC signal out of a 50 hertz or a 60 hertz source, then you will have the ripple's frequency will be that 50 or 60 hertz. So now if you see, right, the capacitor has a finite DC voltage. Right? The capacitor has a finite DC voltage. Average value of the capacitor voltage is finite. So can I then say Q average, the average charge stored across the capacitor is also constant. Is that right? Can I say that? Because the voltage, there is a finite voltage. Therefore, I can say there is an average charge stored across the capacitor. That's also constant. What's happening? There is some increase in the charge and then there is a decrease in the charge. So what's happening here is that if you look at this circuit, when your input signal, say I'm drawing the steady state waveform, not the first clock cycle. So steady state, the waveform looks like this. Okay, so this is your input sinusoid. Your input sinusoid goes like this, and then it returns back. So forgive my drawing there. It goes like this and so on. Okay, so what happens here is that for this small duration, something interesting is happening in the circuit, and during the remaining duration, something else is happening in the circuit. What's happening in this region? The voltage across the capacitor is slowly decreasing, which means it is losing charge. The capacitor is losing charge through the resistor. Okay, the resistor is discharging the capacitor. When the voltage goes slightly lower than the input voltage, when the diode is turned on, instantly your input voltage charges the capacitor. It will charge the capacitor at this point, right? So your voltage is instantly charged back by the input source to its full voltage V peak. So whatever charge that this guy lost in this duration is supplied back in this duration. Is that fine with you guys? See, it started off from VP volts. Its voltage slowly dripped because of the resistor. Then at this point, your output voltage becomes smaller than the input voltage, and immediately diode starts conducting and input starts charging the capacitor. Remember, input is also providing some current to the resistor also, because resistor is an instantaneous element. The moment any voltage appears across it, it will draw some current. So it is also drawing some current. Resistor is constantly drawing some current. But here, what's happening to the capacitor is it's receiving charge in this small duration. In this small duration, a peak current flows through this capacitor. And in the rest of this duration, it is losing some charge. So I can say a capacitor, see, or you can look at it immediately. At this point, the instant diode turns on, capacitor will offer very low impedance. So all the current that the source has to offer will quickly, large current that the source has to offer will quickly flow through the capacitor. Will quickly flow through the capacitor and it will be charged to V peak volts. After that, resistor will slowly bleed out a current. Okay. So that's what's happening in the circuit. So if you look at the capacitor waveform, if I ask you to plot the current through the capacitor, how will it look like? It will look like a huge current at this instant. When it is turning on, diode turns on, a huge current comes through this. And for the rest of the duration, the current's direction will be opposite because it is losing charge. It will be a constant or, some small expressive. Whenever you have a capacitor and a resistor connected in parallel, it will be an exponential discharge. If V peak is the initial voltage, it will be V peak e power minus t upon tau. Okay. But if your time constant is much greater than the time interval t, where let's say t here is one cycle, maximum discharging that can happen in one full cycle is what? Vp e power minus t upon tau. This is the maximum discharge that can happen. But I'm assuming that your time period is much, your time constant is much greater than the time period. Okay. Time constant is much greater than the time period. So this number will be close to 0. I can approximate it to 1 minus x, right? E power minus x is 1 minus x. So it will be 1 minus t upon tau. So it will be like a linear discharge. Okay, so that's why I've shown the waveform. It looks like this. It will look like this. In this time, capacitor is getting current. In this time, it is bleeding current to the resistor. It's slowly giving away current to the resistor. So the waveform of the current will look like this. It will be positive, negative, then a huge peak positive, negative, and so on. Now, keep this in mind. If the average current, see, let's say you have this capacitor and a resistor circuit like this. If I tell you the average current flowing through the capacitor is greater than 0, what do you think will happen to the voltage across the capacitor? Just use some basic intuitions. If I say that the average current across the capacitor is greater than 0, what do you think should happen to the voltage across the capacitor? No, forget about not possible. What do you think should happen? Ideally, the capacitor voltage will just start increasing linearly, right? It will always rise. Or if I say that the average current is less than 0, it will always keep decreasing. It will either rise or decrease. And output voltage cannot go greater than V peak. Your diode will turn off. There is no other path to provide charge for it. Similarly, if your output keeps decreasing, if your output capacitor voltage start decreasing, then the input will start charging it. Even that is not possible. Because you have assumed an ideal voltage source, it will ensure that the voltage across the capacitor is VI. Even that is not possible. So even though your voltage looks like this, it's looking like a ripple. The average value is finite. Okay, it is having a finite average value. If it has a finite average value, it means that the average current flowing through the capacitor has to be 0. What does that mean? Whatever charge that the capacitor has gained in that short duration, it will lose all the charge in this duration. Or I can say otherwise, whatever charge the capacitor has lost due to the resistor, it will quickly gain all of that in a very short duration. So if you have current and charge, how is charge and current related? Rate of change of charge is current. Now charge is integral of current. So the area under this curve, in the small duration, your capacitor current will be positive, and for the rest of the duration, your capacitor current will be negative in such a way that this area will be equal to this area. So this is, I'll call it Q lost, and this as Q gained. And then you have Q average. That's the average charge stored across the capacitor. What is the average charge stored across the capacitor? If you know V average is the output average voltage, so V av times C, that is the average charge stored across the capacitor. That will remain constant. That is always constant. That's what's giving you this constant average value. But it will keep varying. The current to the capacitor will have a zero average value, but it will have a positive, it will be a sudden positive value in very short duration of the cycle, and for the rest of the cycle, it will slowly bleed out the current. So this was the question. I'll recall, I don't exactly recall what the question was, but something like this. You had a capacitor and a resistor. In the problem, it was given, I think this was a 10-volt peak signal, and I think the resistor was 100 ohms. Okay, the resistor was 100 ohms. They asked to compute what is the average current that the diode supplies. Okay, the average current that the diode supplies should be equal to the average current that the resistor draws, right? Only then the voltage across the capacitor will remain constant, right? Otherwise, your voltage across the capacitor either increase or decrease, which is both are not possible. So the average current that is drawn from the input has to be exactly equal to the average current that the resistor draws. So, and it was given that it's a 10-volt source. And I think if I remember right, the time constant, I'm not sure. I think the time constant to time ratio was, time period ratio was, the time constant is much larger than the time period. So T by tau happens to be 20. I think it is 20 or 40, right? So your time constant, sorry, 1 by 20. 1 by 20 or 1 by 40. So the average value, I can use a linear approximation. So 10 e power minus t upon tau, the linear approximation for that will be 10 into 1 minus, or you can just compute how much value it goes to at the end of one cycle. If you assume 10 is the peak, if you assume a purely resistive discharging with a large time constant, then it will lose a charge, lose a voltage, and it will reach P e power minus t upon tau. That turned out to be, I think, 0.95 volts. So from 10 to 0.95. So the waveform will look like this, 10.95, 10.95. So what is the average value? I can approximate this average value to 0.975. Okay, or 9.75 volts. That's the average value. Is this fine, guys? I just wrote 9 points because the linear variation. I've just taken the average of 10 and 0.95. That will be the average value here because it's a linear waveform. I've approximated it to a near linear waveform, and I'm assuming this is like almost a step. So if you have a waveform like this, okay, a step waveform, and then like this, then the average value will be equal to this, the average of these two max and min values. So that is 9.75 divided by R is the average current drawn through the diode. That's it. No, it's 9.75. I'm sorry, not 0.975. See, it reduces to 5% of its initial value, 9.75. So the solution should be 9.75 divided by 100 or 10 ohms. I don't remember the exact values. So this will come out to be 1 by 10, close to 0.975, right? 0.0975 amperes is the average current that the diode provides. Okay, so that's what the problem was, and you didn't have to solve it. The values given were like this. If I remember right, I think the solution was they had given it as 0.1 amperes. They didn't even take this 0.975. They assumed the time constant is so small, I can approximate this value to 10 volts itself. Not much is getting discharged. Capacitor is not discharging much. So the resistor value will remain close to 10 volts itself, approximately 10. So 10 by R should be the average current that the diode supplies. Okay, so that's how you get this result. But you have to be very careful. The current through the capacitor will look like this. It will look like a small peak, and then constantly it will look like this. This peak area will be exactly equal to the area of this curve. That's how you maintain average charge equals 0. Average charge equals to constant. This is, average charge is always constant. So that's how you get that result. Fine. So it's a very interesting problem. You didn't have to go through the mathematics to solve it. You just had to use this concept that for capacitor to have near constant voltage, the average current through the capacitor has to be 0. So therefore, the average current of the diode has to be exactly equal to the average current of the resistor. If you equate the two, then, and if you, the average value of the output, they have, ideally, I would have preferred an answer of 0.075. You just find the average value of which is 0.9.75 volts. Assuming you start off at 10 volts, you discharge to 5% of its value. 0.95% or 0.95% of its value, it discharges to. So the average will be 9.75 volts. If you use that, great. But I think they didn't even expect that. They were expecting to give a number close to 10 volts divided by R, which was 0.1 ampere. Same holds true if I have a current source. If I put a current source here, I, and a diode here, okay, and then I connect, assume this diode, the current source is not large enough to bleed the capacitor fully. It will bleed linearly. It will bleed the capacitor linearly. And suddenly when the diode turns on, okay, you can assume whether it can be a sinusoid or it can be a ramp waveform like this. Okay. Whenever your diode, there will be a brief moment when the diode will turn on, quickly charge the capacitor to the desired voltage, and then it will bleed like this. The same concept holds true here also. If you assume this peak to peak is really small compared to this average value, you can treat that the average current of this diode will be exactly equal to I. So that was the idea behind it, and I thought it was an interesting problem to discuss.